Hi guys, let's break down the quiz problems that we looked at this week. So this was really useful for me to get a little bit of a clearer picture as to how people are thinking about the stuff that we've been working on. So there's definitely a spectrum of how much people are comfortable with the material. So I think maybe we'll do something like this every week where we'll look at a problem or two just to kind of see, make sure everybody is doing okay. So uh, this first question, we have a charge Q applied to a conducting sphere of radius r naught. So we want to know, A, sketch the electric field magnitude as a function of r. So what I was imagining for this was just a cartoon like this. As a function of r, what does the magnitude of the electric field look like? Well, since this thing is a conductor, there will be no electric field inside of it. So it's going to be 0 up to r naught. And one way to convince yourself of this is that so remember, in a conductor, the charges can move around. They can move around easily. They're free to move. So if there were an electric field inside of it, those charges would feel that electric field and they would move. So what's going to happen is the charge, since it's free to move, is going to accumulate all on the surface. You can think of it as the charges are trying to get as far away from each other as possible, so they're going to end up on the surface. And so there will be no electric field on the inside. And then outside of it, it's going to look like, since it's spherically symmetrical, it's going to look like a point. So it'll look like 1 over r squared. And this is basically what I was looking for your sketch of what the electric field magnitude looks like. And then for part B, where I'm asking you for the function, there's a couple different ways that we've talked about to think about this. One is, if you know it's like a point charge, you can just say, oh, okay, well, it's gonna look like Coulomb's law. So it would be, the electric field would look like kq over r squared, and this is pointing in the r hat direction. So since it's a positive charge, the field is pointing away from it. So, and imagine that's, spherically symmetrical. So one argument for this would just be to say, it's going to look like a point, see Coulomb's law. The other way that we've talked about this is you can use Gauss's law, and you can say, okay, well, if I look at E dot dA, it's going to equal the charge enclosed over epsilon naught. You can imagine drawing yourself a Gaussian surface that goes, around, a sphere that would be concentric with our spherical charge distribution. And so this would look like, now remember, since the electric field and the area of that Gaussian sphere, the area elements, are going to be aligned because it's a sphere as well, this becomes E just an integral over the area. And this is just the area of the sphere. And so you get the same thing, that your electric field is Q, oops, I dropped our epsilon naught here, over 4 pi epsilon naught r squared. And this is also, it's pointing in the r hat direction. So two different ways to describe or to come up with the expression for the electric field for a spherical situation. And this is kind of what the field would look like. So for conductor, so that's sort of more of a knowledge question at this point. Our other question was on vectors. And I know this is an area that we need to work on, so I wanted to assess how we were doing with it. So let me pull up this question. So we have a charge located at the origin and a charge at point negative d, 0 along the x-axis, and we want to know what the electric field is doing at 0d, so on the y-axis. So a student pointed out to me today, this is kind of ambiguous because it says up here negative q, and down here q and negative q. I am sorry about that. That was not my intention. It's a typo. I had intended this to be q and negative q. We'll work it both ways so you can see what effect that would have. It changes things a little bit. It will flip a sign on us. Okay, so how do you approach this? Well, the first thing that I would recommend is to draw yourself a picture. So I was a little disappointed not to see more cartoons of what's going on. If you're looking at this point where you want to know what the E-field's doing, from the negative Q, you would have this. So you could think of that as like E negative Q, however you want to label it. And then from the positive Q, you would have, so remember, it's going to be pointing along the line between them. So you would have something that's pointed like that, exactly, like something like that. And it's a little bit farther away, so this one would be a little bit smaller. So this would be E, plus Q or whatever. Okay, so that's roughly the two components that we're going to need to add together. How do you add them together? Let's look at X and Y. So if we look at the sum of the electric field in X, what are we going to have? Well, it's just going to be the component of this that's in X. So maybe we'll call this one E plus QX. And so there's different ways you could define this. Probably the easiest way is to think, okay, this is an angle theta. So what is that going to be? Well, we know the electric field for a point charge is going to look like KQ over R squared. R squared in this case is going to be the hypotenuse of this triangle. So since it's equal lengths on the side of the triangle, we know that this is going to give us a factor of root 2. So this would look like square root of 2 times d squared. And then we would multiply this by, we just want the x piece, so this would be cosine theta. And we know that that angle is going to be 45 degrees because those lengths are the same. So maybe you're thinking about this as 45 degrees. I saw some various ways that people had interpreted this. But you could also recognize, your 45 is a special triangle. So this will be 2d squared, and you could write this if you wanted to as root 2 over 2. And we could recognize that this is the x piece, so this would be an I hat. And that's the only contribution that we have in the x direction. So in the y direction, what do we have? We've got kq over d squared. So now our distance is, well, we're going to have two pieces, but the contribution from the negative q would just be kq over d squared, and that one would be negative. It's pointing down. And there would be no angle. It's all in y. So it's this chunk. And then we would be adding to that the positive contribution from this one. So you can think of that as this piece. And that would be, E plus Q, the y part. So what would that look like? That would be KQ. Again, we'd have this factor of 2 in the denominator because it's farther away. And times sine theta. This will be the same. So we'll pick up, well here, I'll leave it as sine theta Um, and but recognize that this would be the same thing, root 2 over 2. And this whole thing is in the y direction, so j hat. And recognize, we could sort of simplify these things. We could pull out this common kq over d squared. So just to kind of make things more concise, and this will help when we add them together. Let's do kq over d squared, and then this would be root 2 over 4 in the I hat. Then this piece, if we factor out the kq over d squared out of everything, we would have a -1. And then here we would have positive root 2 over 4. And this would be in the j hat. Okay, so these are our x and y pieces. I was a little bit vague, it occurs to me, stating this question. The net electric field is just the sum of those, the total. So you could just state it as these components. It's this much in I hat and this much in j hat. But kind of what I should have been more precise about is I wanted the size. I wanted the magnitude of this. So if you want the magnitude of this thing, really what you want to do is you have to add the components vectorially. So we would want to do ex squared plus ey squared, that quantity square root. And we can set that up. So what would that look like? We would have, it's going to be various stuff here. We would have a kq over d squared root 2 over 4 plus kq over d squared times this thing. Actually, let me just make this one term. So this would be -4 plus root 2 over 4. And that thing squared. And we were taking a square root of this whole, I'll put it in a bracket. Take a square root of that whole thing. So this looks kind of messy, but notice we can pull out this common factor. So this kq over d squared is common to both terms, and then we would take a square root of it. So in other words, we can pull that piece out of the square root, and we're left with this stuff. So we would have root 2 over 4 squared plus -4 plus root 2 over 4 squared. So this is just a number. This is a pretty reasonable way to state this. Although I can simplify this further for you just to show you, if you wanted to, how you could, make this a little more concise. But that's basically what I was trying to get at, is recognizing adding vectors, how you add the components, add them in x and y. If you want to find the magnitude, you have to add the vector components together. It can get a little bit cumbersome, but basically if you had something that showed this, that's great. Some folks had this even, further simplified. You can see that this, this would cancel down. Here, we can do that right now. Let's break it down a little bit more. So this we would have just 2 over 4. And then here we would have to expand this thing. So we'd have 16. Oh, wait, no, not 4. This would be 16. We'd have 16 minus 2 times 4 times root 2 plus 2, and this would also be over 16. And then you can see we could add this stuff together. So this would give us kq over d squared. Let's see, 18, 20. We'd have a 20 minus 8 root 2 over 16. You can see we could, oh, I forgot our square root here. We could divide out a factor of 4 out of all this stuff. So actually this would boil down to a pretty concise just 5 minus 2 root 2 over 4 square root. So that would be a more concise way of, stating the electric field magnitude. And you could take the, actually evaluate that, find a number. So that's basically what I was getting at. To this ambiguity about the charge, let's amend this to be as if that positive charge is negative and see how it impacts things. So let's make this one negative and see what happens. So before we had been doing, actually before I do that, before this vector addition had been, basically there was a piece that was pointing down, and then we were adding a piece that looked like this. So you can add your vectors by head to tail, just to kind of give us a picture of what it would look like. So we know that the net would look something like this. Now, if we make this one negative, what's going to happen? Well, this E plus Q would be pointing instead towards the charge. So now, instead of this picture, we would have, this one would be going the opposite direction. And then when we add our other one, it would look like that. So the net would look like this. The picture's kind of not that good. Let me try and draw this a little better. So it would be like the one at 45. We would add to that the one that's pointed straight down. And so the net would look like this. You can see a couple differences. It's pointing in a different direction. And it's also, it's a little bit longer. So let's see what effect this would have on the math. So notice we would pick up a negative sign on our x component. So this would become, there would be a negative here. And we would also pick up a negative sign on our y piece. So they actually would both be negative. And what effect ultimately that would have is, notice when you go to add them together, since you're squaring the terms, that negative sign doesn't matter on the x piece. On the y piece, you could pull the negative sign out of both, and then it would go away. But what it would mean is that the result where we have this negative sign, that negative would go away. So this would become, for the case where they're both negative, we would lose that negative sign in the numerical factor. And you can see the effect of that. That would make this is bigger than this. So yeah, sorry, I did not notice that typo until someone pointed it out to me. So I guess that's a lesson too. If you see something in a question, don't hesitate to ask clarifying questions. But hopefully seeing the impact that has on analyzing the problem is a useful exercise too. So looking at the electric field, adding vectors, definitely some things that you have to have command of as part of this course.